Good morning, everybody. Welcome back to class. Before I get started today, I wanted to mention a couple things with the homework. So just a few reminders. We've had 2 homework sets due, I think. So I just took a look at the average grades. They're almost like perfect scores. So like 5.9 out of 6 for the first one, like 4.9 out of 5 for the second one. There's going to be a couple extra credit assignments. If you lose a little bit of points here and there, you should be able to earn some points back on some extra assignments. The max homework score, unfortunately, will be 100% though. So it won't be extra credit you can apply to other areas of the class. But just make sure if you haven't seen the homework or aren't aware of it, that it's through the MyLab and Mastering course code and Carmen. Follow the start of term tasks if you haven't got that set up yet. One thing I also want to mention with the homework is like using it as a chance to get some assessment on your learning. I think it's possible the questions are kind of easy. There's actually places in the book you can actually find the answers, but it's somewhat intentional for you to pay attention to the readings, go through those. You can look at the self-assessment questions as they pop up in the readings, and then notice that those questions are mostly the basis of the homework sets. The homework set should give you a chance to kind of quiz yourself or assess your learning, just so that you're really solving problems really authentically as you go, or at least trying to get into the mode where you're practicing problems with the book closed, notes closed, using what you've learned in the class so far. Okay, so we're getting into sig fig calculations last time. We're going to do some more of those today. Before we get into some problems with significant figures, let's look at precision and accuracy and kind of the difference between the two terms. And so the preciseness is how close measurements might agree. If you're throwing darts, it's if you're aiming for the bullseye, it's hitting the bullseye. So preciseness is trying to hit your target repeatedly. So how close are you getting to the target every time? Accuracy is like you can imagine maybe we have 3 throws and darts in a row that all hit the 20, like the double 20 spot. So maybe we have 3 measurements that all hit in this region over here. And so if we're hitting over here, but we're aiming at the bullseye, we had great precision, so our measurements were all on the same point, but they were off target, so they were off the accuracy of the target. So if we're hitting our target, that's accuracy. If we're just repetitively making the same measurement, that's precision. And so how does this relate to laboratory work, working in the lab? It would be the sort of idea that if we're going to do a procedure, we might carry it out a couple times to see how precise and how agreeing our results are with each other. And that might help us test to see if we're making a mistake. So maybe if we're making a mistake in one trial and not the next, we can pick that up by our trials being really off from each other. But if we repeat an experiment a couple times, we're getting the same data each time, we may then say, well, how well do those results agree with some established standard? So maybe we test the procedure out to determine some known value that we already know. So maybe we're supposed to determine that some compound has a molecular weight of 100 grams per mole, and then we get 99 grams per mole once, we get 101 the next time, we get 98 another time, averages out pretty close to 100, so pretty accurate, pretty precise. But let's say we do the experiment a different day, or a different way, or a different type of experiment, and we're supposed to get 100, and we keep getting 75. If we keep getting 75, we're off target, so we have maybe still good precision, maybe we're still getting close to 75 each time, but we're supposed to be getting results closer to 100, so we're not accurate. That might mean that the tools we're using aren't calibrated correctly. It could mean that we're making the same mistake every time. That could be possible too. But it could be that maybe some tool that we're using just is miscalibrated. So it can help us understand some of our lab measurements in terms if they're on target with what we're trying to shoot for, that's accuracy, and just repetitively obtaining the same value, that would be precision. And sort of the precision is what sig figs is getting at. So sig figs is really trying to be a measure of whenever we take a lab measurement, that the measurement itself carries some inherent impreciseness. And that impreciseness is related to how many digits we see on the value. Or if you're using a balance, you can kind of see where it's drifting up and down. It's that drifting up and down point for that uncertain digit. So let's look at this question here. So to the proper preciseness, or another way of putting that is the number of significant figures, what is the density of an object that has a mass of 50.00 grams, which displaces water in a beaker from 75 to 125 milliliters? Now, for this type of problem here, the numbers mean something. The fact that we see 75 milliliters here is telling us that that last digit in the number is the uncertain digit. That's the one in that lab measurement we're interpreting to have been the digit that was uncertain. If you're using a beaker, it's actually really hard to measure the markings. So if you can imagine trying to use a pretty big beaker to measure 25 mils, you're going to have a pretty big plus minus. You're not going to really be certain that it's 25.00 milliliters, probably 25 plus or minus at least one, if not like say 5 milliliters. So when you're looking at the 75 and 125 milliliters, your plus minus is pretty big here. It's going to be at least 1. So it's going to be greater than or equal to 1 milliliter in terms of our presumed uncertainty in the measurement of that 75 mils. The same thing with the 125. It's that impreciseness in that measurement that we're going to have to understand and track through the problem. It's going to limit how well we can know the resulting density of this object. So we're calculating the density of the object, the grams per milliliter, so that's mass of the object over the volume of the object. So we're determining the volume by displacing water. So if you have water in a container and you put an object and it completely submerges the water and the volume changes, you can take the displacement of the water to determine the volume of the object. So our mass here would be 50.00. We were talking about sig figs last time. You might remember we were counting sig figs. So 50.00 would have 4 sig figs, right? So all of the zeros are significant. That 5 in the value is significant. So all these values are significant here. So we have 4 significant figures. Those zeros wouldn't have been written if they weren't significant. Okay, so 50.00 grams is just a different number than 50.0 grams. It's different than 50.000 grams. Those have different preciseness in the laboratory that would have been taken to determine those measurements. So 4 sig figs for 50.00. Now what's the volume here? So the volume would be 125 milliliters for the final. Then we originally had 75 mils of water. So the object had to be 50 milliliters to displace the water by that amount. But 50 to how many sig figs? To 1 or 2 sig figs? Or 3 or 4? Well, if I just look at 125 minus 75, I get 50. It's all about where the placeholders happen to fall. Let me do the problem with slightly different numbers, just in case you're not going to agree that this is 2 sig figs. If I had 126 mils of water, and initially it was 51, so let's imagine we had a different type of beaker that had markings at 26 mils and 126 mils for some reason. We had a weird beaker that had these markings instead. Let's say it had even weirder markings. Let's say it had a marking at 27 milliliters. And for some reason, we could see that the object was displaced from 126 to 27. So really strange beaker. So instead of having a 25 mil line, it had a 27 mil line that we could kind of see that the water was filled up to. And then instead of having a 125 milliliter line, it had a 127 milliliter line. And presumably the beaker was calibrated so that that was roughly where those markings were intended to be drawn. And so now when I take this difference here, so some different problem, this maybe is what our displacement would have looked like. What would the volume of the object have been, and to how many sig figs would you think it to be? So I think it would be 49. That's stupid math, right? No, 51. I can't do math on the fly. Oh, I was closer to 75. Let me make this 77, just to keep the numbers kind of more in line with the previous example. So it comes out closer to 50-ish. So 125 to 75, and then we had a goofy beaker. The markings were at 126 and 77 mils. And so we take our difference there, and that would be 49 milliliters. Now, what I'm trying to get us to see is that I don't think we would disagree that 49 has 2 sig figs in just the problem of 127 milliliters minus 77 milliliters, and trying to think of some weird scenario where we might have used a beaker to come up with those measurements. And so I don't think we would disagree that this has 2 sig figs. And if we're not going to disagree that this has 2 sig figs, then I don't think we should disagree that this has 2 sig figs either. Because sometimes when we look at this problem here and we just have numbers that end in that 0, and we do 125 minus 75, we see 50 in our calculator. Sometimes we think back to the rule where if in some other context, if the problem said you had a 50-gram object, you would probably interpret that as 1 sig fig. But that's a different context. We didn't know where the 50 came from. If you have a problem where it says a 250 milliliter sample we're interpreting that as 2 sig figs, not as 3. So is that 0? If I just see in some context in a problem, if I see 250 milliliters for an object, I'm looking at this saying that this is 2 sig figs. But that's a different scenario than having a math problem that led me to a result of 50, where I had 125 to the ones placeholder, 75 to the ones placeholder. Our multiplication and subtraction rule says I should round the result to the same placeholder or decimal place as the value of those measurements that had the fewest placeholders. And so that's going to be the ones placeholder for both of them. So I round this result to the zeros, so that, ones position placeholder. And so that is why I have 2 sig figs on this quantity, not 1. Same thing, if I had 125.0 minus 75.0, then this would be 50.0 for 3 sig figs. Because again, it would be tens place minus tens place, I round to the tens place. And the whole reason for this is just where your inherent or your presumed uncertainty lies in these measurements. Whenever we have 125, the presumed error is at least greater than 1 milliliter. So we have at least 1 milliliter of error in the 125, at least 1 milliliter of error or uncertainty in the 25 milliliters. In the case of a beaker, it's going to be even greater than that. So that's just like the minimum error, or the minimum uncertainty. That uncertainty would track through and keep that uncertainty in that ones placeholder. That's kind of why the sig fig addition rule works the way it is. And so for addition, subtraction, it's all about kind of lining up your decimal place and looking for the greater quantity or value placeholder and rounding to that particular placeholder. Now, for this problem here, we have a value with 4 sig figs divided by 2 sig figs. So how many sig figs should I keep? The math is simple. It's just 50 divided by 50. But I should keep 2 sig figs. Because now I'm doing a division step. When I do 50.00 divided by 50 with 2 sig figs milliliters, so I have 50 milliliters, 2 sig figs. I have 4 divided by 2. The multiplication division rule, we talked about this last time, is we count sig figs when we multiply and divide. If I have a 4 significant figure value divided by a 2 significant figure value, I would round to the lesser number of sig figs. I'd round that to 2 sig figs. And so that's how we can see how we round values off, especially when we do the math in our calculator and we get a whole number. So if I get a whole number of 1 here, the density, like a density of 1 gram per milliliter, has a different meaning in a science or laboratory context than a 1.0 gram per milliliter sample. That has a different meaning than 1.00. So it takes a greater amount of skill, lab work, glassware quality to get those extra decimal places onto a value. Let's actually look at the different way we might carry out this same problem. To kind of exemplify the way sig figs works. So the first example, we're using an ordinary beaker. You can see the problem with the beaker would be how well can you really know the volume at the increments. So even if you're lined up really well on that dash, it's not 25.000 milliliters. It's really hard to measure precisely 25 milliliters. You might have to use one of those pipettes. You might use these in the lab where you have like a 10 or maybe a 25 mil pipette that has a really skinny tube at the very top of it with a marking very easy to kind of get your meniscus lined up on, such that when you deliver that quantity, it's going to be really, really precisely 25.00, usually 2 sig figs of accuracy using a pipette. Now, another tool we can use that has a little bit greater precision is a graduated cylinder. So we can fill a graduated cylinder with water. If the object fits in it, we can displace water in mostly the exact same kind of fashion, and then get a more precise determination of the volume before and after the adding of the object. So we can do the same problem that we did before. On this problem here, we even used a better balance. So we now have, instead of the 50.00 gram, we use an analytical balance. We determine it's closer to 49.9724 grams. And then using the graduated cylinder, we notice that the water goes from 75.5 to 124.0 grams per milliliter. And so let me have you guys work on this problem here. You can work on it by yourself, or you can work with your neighbors for maybe like 2 minutes just to think about what is the density and how many sig figs does it have. All right, so let's take a look here at this one. So we now used a different tool. I think the one thing with sig figs is separating the idea of applying sig fig rules isn't trying to change arithmetic, but it's just dealing with the arithmetic of measured quantities. So it's when the arithmetic is involving ordinary lab measurements or measurements we're assuming were recorded with lab equipment, where we're just noting that the last digit in each of these values is carrying some uncertainty, and then based on where those placeholders fall and the number of sig figs in the values, that's going to limit the preciseness of our results. So that's where sig figs are playing a role. And so we now have we also have the idea that this object has some density. It has some true value for its density that we're trying to determine here with lab measurements. But the key is that how well we can take those lab measurements is determining how well we can establish and know that density. And so anyways, we've taken a more precise mass, which is actually probably almost a waste of time, right? Because we went from 4 to 6 sig figs, and this really wasn't limiting our preciseness. So we've fine-tuned one detail of the experiment that maybe we didn't need to do, because we're still going to end up rounding based off the number of sig figs on the volume. If we had used the previous 50.00 grams, we would have obtained mostly the same density. But now the volume is 48.5 milliliters. That extra tenths place of the ability to read off that volume gains us an extra sig fig on knowing and establishing the density of this object. And so for this quantity here, 3 sig figs. For addition and subtraction, just line up the decimal points and do the arithmetic very carefully. So when we apply a multi-step calculation, we apply the rules of sig figs in the order that we do the math steps. So when I'm doing the subtraction first, I carry out the subtraction step, get my 48.5 to 3 sig figs kind of first, because that's the first math step I kind of needed to do. Then I have 6 sig figs divide by 3, and that ends up giving me the 3 sig fig answer. Though I think it should be 1.03 and not 1.02. But 3 sig figs for the answer. And so one of the other keys is that it's really not, if you looked at this problem and said, oh, this has 3 sig figs, so the answer has to have 3. That's not exactly always going to be the case. And so we'll see some examples where you just have to carry out the subtraction step and see how many sig figs do you get here. That ends up being the limiting number of sig figs in the step, not specifically, because the reason why 48.5 has 3 sig figs here had nothing really to do with 75.5 having 3 sig figs, but just the result of that math step having 3 sig figs. And so sometimes when we multiply and divide in a problem, we want to look for that least number of sig figs. That's not always going to be the answer. So we have to be careful when we add and subtract to use addition subtraction rule correctly. So we use dimensional analysis a lot in chemistry. We've used it already. Dimensional analysis is really just a problem-solving tool for converting units. And so we can go from like grams per milliliter to kilograms per what's a good unit? Kilograms per milliliter, maybe the liter, to gallon, to other volume units. So you can convert units to and from each other using dimensional analysis. And you'll see that this is often a problem-solving tool, just so that any time we have problems that just relate to unit conversions in some sort of a way, or equations that relate units, a lot of times you'll see us using dimensional analysis to help us solve those problems. So let's look at a couple dimensional analysis problems. And so this one here is looking at 14.75 inches to centimeters. We're given the conversion I mentioned. Most of our non-SI to SI conversion factors are given. I think the only time you really need to know the conversions are using prefix conversions. We mentioned knowing giga, mega, kilo, centi, milli, micro, nano, and pico. And so just knowing those conversions, those kind of go in order of 9, 6, 3, and then centis -2, millis -3, micros the -6, 1 nano -9, and pico -12. So, there's not a whole lot of values. They're somewhere between, 10 to the +9 to 10 to the -12. The only one not on an increment of 3 is the centi. So not too hard to kind of recognize those, and probably remember those from some of your past work as well. But so when we're converting inches to centimeters, we have that conversion given. Now, this is really actually more of a sig fig question, also a very, very short and easy dimensional analysis problem. And so let's actually do this one together because it's pretty straightforward. So if we're starting a dimensional analysis problem, dimensional analysis, I always try to start with what we're looking for. So we're trying to determine the number of centimeters. And then we're going to begin the math step with the information we were given, some piece of the given information. And the only times, like on a harder dimensional analysis step, is trying to think if given information needs to be on the top or in the denominator of the equation. And so usually the worst case of a dimensional analysis problem is needing to like flip everything if we end up getting like the inverse of some value of what we were looking for. And so we may need to maybe do a problem kind of once and see that we needed to flip some conversion factors around. But this problem here, pretty straightforward into starting with 14.5 inches and just using the 1 inch to 2.54 centimeter conversion. But this is an exact conversion. We're actually told this in the problem. This is an exact conversion, meaning that 1 inch is exactly 2.54 centimeters. This is the same meaning as like a foot is exactly 12 inches. It's not like 12 plus or minus 1 inches. It's not one of those conversion factors where we're looking here. This is not 3 sig figs. This is like an infinite number of sig figs. Remember, sig figs applies to ordinary lab measurements that are subject to some impreciseness about their measurement. It is not just about ordinary numbers having some significant figures. Like if we go back to having 12 people that we count in a room, we have exactly 12 people. We don't have 12 plus or minus 1. We have exactly 12 with infinite number of sig figs. So if I count 12 people, I have infinite sig figs. I don't have 2 sig figs in that number. Sig figs are for ordinary lab measurements or values we're assuming were obtained using equipment where we have some inherent impreciseness. Like 25 milliliters, that's assumed to carry some uncertainty, so this is 2 sig figs. But 1 inch to 2.54 centimeters, as an exact conversion, these are both infinite number of sig figs. So when we do this math, we actually keep all 4 sig figs. So, because part of the problem is like how many sig figs should the result of this conversion be? Let's actually do the math. It wasn't asked, but let's just do the math real quick and just remind ourselves the inches are canceling. We get centimeters. So 2.54 times 14.75 is 37.465 is what the calculator says. I'm going to round this to 4 sig figs. Why do I keep 4 sig figs? Well, I have 4 sig figs here, and I have an infinite number, a perfect number of sig figs, an exact conversion. I'm not going to round off to 3 sig figs because the 2.54 doesn't have 3 sig figs. It's assumed to have infinite sig figs. If we're rounding because of a conversion factor, then either A, we've done way more precise work than whoever it is that defined the conversion factors. Doesn't that seem strange? Also seems strange if my screen is gone. This whole semester. Why is the middle? People will watch this video later, like, what's going on? The projector screen is not working. Why is that one working and not the other two? This is... What the heck? All right, I'm powering them off, and we'll see if we can turn back on here in a minute. Okay. So let's talk rounding for a second. Yes. Well, I guess, so there's a difference between saying, like, let's say you determine the length of some object is 2.54 centimeters. That's a different thing altogether than saying the inch is exactly 2.54 centimeters. You know, so like if we're using a ruler to determine the length of some object and we get its length as like whatever it is in centimeters and it happens to be 2.54, then that's a different interpretation. So that's like 2.54 is an ordinary lab measurement plus or minus 0.01 at least centimeters, has some inherent uncertainty. So if we determine the length of an object, again, I thought I turned the projectors off. I don't know why they're still on. All right, there we go. But that one didn't turn off. But there's a difference between defining a conversion factor a certain way and taking a measurement a certain way. So anything we take as a measurement has some inherent impreciseness, and then a conversion factor is just a definition. Think of another conversion factor. Like if we were to convert, say, 25 centimeters to meters, so easy conversion, 25 centimeters to meters, 100 centimeters per meter, so it's 0.25 meters, right? Well, we don't ever look at that and say 100 centimeters in a meter. We don't ever look at that and say that that's 1 sig fig. Right? We would never look at the 100 centimeters to meter and think that either one of those values is representing just 1 sig fig. Those are both infinite sig figs. So however many meters or centimeters, however many sig figs we have in that quantity, times dividing by 100 centimeters, we would keep all those sig figs. Does that kind of help? Another thing is, like when we look at 1 inch to 2.54 centimeters, the 1 inch doesn't have 1 sig fig, right? Like we don't look at the 1 inch and say that that has 1 sig fig, so we should round because we multiply by an inch to 1 sig fig either. Let's see if this at least turns both of the side ones on. I really don't know why the middle one didn't turn off. Okay, so I was gonna talk briefly about some weird rounding rule and I could use chocolates too. Yes.
So, are conversions always exact and always have infinite, like any conversion?
Conversion factors have basically 3 different scenarios you can have for a conversion factor. So the question is, are all conversion factors exact? And the answer is no. Some of them are based off of other conversion factors that are rounded, but most are known very precisely. So like the pound to kilogram is a good one. If you, does anybody know the pound to kilogram conversion off the top of their head? 2.2. Yeah, 2.2, but it's like 2.2046, but it's actually 2.2046 with like 10 other digits if you want to look them up. So most conversion factors, we may know them a certain flavor that we could look up more precisely if we need to use them. So like if we're using a conversion factor in the lab, what I would do is if some mass value I have has like 5 or 6 significant figures, and I'm using a conversion factor that has less than that, I may just go look up the conversion factor. I think on the daily quiz area of Carmen, I have an equation sheet that has almost every conversion factor you would ever need to know with a bunch of digits, with a bunch of preciseness, and as much as are known for most of those values. And even some of them are marked. I know I went through and did this one day. They're marked with the ones that are actually rounded off and the ones that are then exact. And some are exact or precisely defined, and others are rounded.
So the ones that are exact is infinite, and the ones that are rounded off is just a number.
Yeah. Yeah, so I guess the 3 flavors was those that are like exact, like 2.54 centimeters, and those are exact because it's a definition, defines that conversion. Others are rounded off, and then others are just like known to a gory number of placeholders. All right, I have 1 projector still. What is going on here? This is... I mean, how much eye strain? Can you guys on this side of the room see that projector? No. I mean, you guys do have the notes in front of you. What the heck? All right, so those online are just going to have to watch. So we'll do a couple problems on the board. I haven't used chalk in a while. You know, before iPads came along, I actually did all my lecturing on the chalkboard. And I haven't touched a piece of chalk since the iPads came around in 2018. But let's do a cubic conversion. So cubic conversions are slightly trickier than a normal conversion, but they use the same basic conversion factors. Like if I'm converting 225 liters to cubic meters, how might I carry this conversion out? So let's write out what we're looking for. step, we know we're looking for cubic meters, and we're starting with what we're given, 225 liters. Now, what might I use here in terms of conversion factors? Well, there's like one conversion factor for volume that sometimes, maybe it's so obvious we forget it, but it helps us with like liters to a cubic length unit, is that 1 milliliter is exactly 1 cubic centimeter. And maybe before this problem you forgot this. This will become so ingrained soon enough that this is such an obvious conversion factor that usually wouldn't be given. But that one conversion factor is really all we're going to need to go from kind of the liter into some sort of length cubic unit. And then we can use our conversion for 100 centimeters into cubic meters. So if I know there's 100 centimeters in 1 meter, I should be able to determine from that conversion the number of cubic centimeters in a cubic meter. So if I know this conversion factor, then I should be able to determine that for 1 cubic meter, so if I have a 1 meter by 1 meter by 1 meter cube, that would be 100 centimeters by 100 centimeters by 100 centimeters cube. So a 1 meter, my ability to draw a cube is, it's not that hard to draw a cube, right? So we have some sort of terribly drawn cube. 1 meter by 1 meter by 1 meter is just 100 centimeters times 100 centimeters times 100 centimeters. And so if each of these is just equal to 100 centimeters, then our conversion for cubic centimeters is just that whole conversion, the 100 centimeters, the whole quantity cubed. Just 100 times 100 times 100. So 1 cubic meter is equal to 100 cubed and then centimeters cubed. So the cubic conversion is just you have to cube the conversion factor, in this case here. So how can we put this into practice in our problem? Well, it's just we're going to have to go from liters to milliliters to cubic centimeters to cubic meters. So how many milliliters in a liter? 1 liter is 1,000 milliliters. Now, we could make a simple one-to-one conversion here like this, if you're comfortable with that, because if a milliliter is just a cubic centimeter, then we can do that conversion really easily. We could always two-step conversion factors, so we can always just leave this in milliliters and then write one more step just to make sure we're seeing the liters to milliliters, milliliters to cubic centimeters. Well, we haven't canceled cubic centimeters yet, but we're about to. And so then we just have to divide by cubic centimeters. Now, if I haven't gone through all the stuff that we already went through on the cubic conversion factor, I may have written this. Which just isn't the right conversion factor. Like cubic centimeters isn't canceled out by centimeters. So in this case here, I'm just cubing the entire conversion. And so then if we just think about math, if we have AB over CD cubed, this is just remembering that this, of course, would mean A cubed, B cubed, C cubed, D cubed when we write this out. And so if I imagine cubing the whole conversion, that just means I can cube everything here. So I cube the 1, of course it's still 1, cube the meters, cube the hundreds, cube the centimeters. And so we're doing 225, converting to milliliters, and then dividing by 100 cubed. And now, again, this kind of comes down to putting it in a calculator. And if we haven't done silly arithmetic like this in a while, sometimes we can make mistakes just by plugging this into the calculator wrong. But 225 times 1,000, that's easy. And then I've seen like divide by 10e3 sometimes. 10e3 is 10 times 10 to the 3, which isn't 100 cubed. One of the simplest things is divide by 100, divide by 100, divide by 100. You know, that will always work. We can divide by 100 caret 3 as well. So 100 and then raise to the power of 3. So you just want to enter this in, 100 caret 3. Or just do 100 carry 3 separately, I think it's 10 to the 9 or something that works out to. But you can do the math separately and divide by that as well. Occasionally we have students miss problems just for knowing how to do the problem, but then the calculator step, we just do something too quick and don't realize we made a math mistake. And so that's 0.225 cubic meters. And so the cubic conversions, there's like always a test question on like doing a conversion kind of like this where you just have to carry out and cube our conversion factors, usually for like cubic millimeters into cubic meters, cubic centimeters into cubic meters, something like this. Now, again, I mentioned problems like this before where you probably could have just gone to Google and typed in, 225 liters to meter caret 3, and it would tell you the answer. Now, homework problems on practice test questions, use the same strategy and tools you have available on the test. So just use your ability to solve the problems at some point when you're practicing these types of questions. That's really easy when I work them out. Sometimes you'll see a little twist in these problems that make them a little bit trickier. Like you can have a problem like this where imagine you're taking a gram per liter to a gram per cubic meter. Same basic problem, it's just everything's kind of flipped. But the dimensional analysis steps still end up being worked out with the same idea. Okay, I had given some extra problems on sig figs. Let me see if some are worth doing. Let's do a couple of these extra sig fig problems here. So one of them was 25.56 minus 8.4. And we're assuming these are ordinary lab major values. Like, you don't see a lot of problems involving sig figs where they just give you numbers, and I feel like that's kind of silly. Like we're really trying to imagine that this is some sort of lab major quantity. Because that's why we have the rules of sig figs. Like I said before, we're not changing arithmetic, we're just changing arithmetic when the math is involving ordinary lab major quantities that have some inherent impreciseness in the last value that was given. And then another thing we have to keep in mind sometimes is that just presumably some different material measure this volume and some other piece of lab equipment measure this volume. And for some reason we're doing math this way. So sometimes we may look at a problem that has mass units with different numbers of sig figs, and we're like, how did that even, why would you have different mass units with different number of decimal places? And the answer is maybe different tools the lab would use to determine those. But just line this up here. So when you carry out your arithmetic, you can just line your decimal place up. It's super easy, right? So if we carry out our math this way here, 17.16, and I need to round to the tens place number. So I'm looking hundredths place, tens place, and rounding to the higher value quantity place number. So 17.2. So 14.5 plus 94.3. Let's look at this one here. Stuck with the third one on the sheet is 14.5 plus 94.3. And we're dividing this by 44.54. Again, all the values are assumed to be some sort of ordinary lab measured quantities. Now, who right off the bat thinks it's 3 sig figs? Is anybody who's just like, okay, it's got to be 3 sig figs? If you think it's 3 sig figs because we see 3, we're dividing by 4, has to be 3. Not always going to be the case. We have to carry out the math. So we have to do the math step first. So how many sig figs does this result have? 4. Yeah, because we pick up, when we do the math, it's going to be 100 something. So 14.5 plus 94.3. We can line this up too just to make sure we see why we're doing it this way. Math, we're looking at our placeholders. So tens place, we're good to the tens place. And so that's 108.8. all 4 of those digits are significant. So I have 4 sig figs in the numerator divided by 44.54. I'm going to keep 4 sig figs, so 2.443. Okay, does everybody see how it's definitely not 3 just because of the way the addition rule works? All right, let me try one more attempt to get this thing to connect. All right, so let's do one more problem together. So on the next page of sig fig activities in chapter 1, let's just look at the third problem down together, because I think these problems do get pretty easy, right? Like the first one, 100.2 plus 25 is going to be 125 for 3 sig figs. If everybody has the notes in front of them. So if you have 100.2 plus 25, that's clearly going to be 125 to 3 sig figs. Then the next, like some of these problems where you get whole numbers out are somewhat times useful to look at, like the 10 divided by 5 in the next problem. Obviously comes out to be 2 on our calculator or just mathematically, but the 3 sig figs divided by 3 sig figs leads that to be 2.00. So we pick up 3 sig figs for that next one. But let's, no, it's actually the same problem we just did, almost, on the next one. So the 25.8 plus the 94.5, same thing there. We're picking up 4 sig figs divided by 4. So it's really just the same problem we just did, but with different numbers. Okay, clearly something's wrong. I just switched to like this document camera thing, and this one's still not working. That one's working. The middle one's a piece of crap. So, it's really funny today. I was really excited that we're going to get into chapter 2 and discuss some parts of chapter 2, because I really need you guys to look along. I know not everybody probably has the notes in front of them. Let me just mention where we're going to get at chapter 2, and then we'll wrap up from there for today, since the projectors are evil. So chapter 2 gets into the topic of atoms, molecules, and ions. That's the title of the chapter. And so we begin with how it is that we began to discover the subatomic particle. So the first section or two in chapter 2 gets at some of the key discoveries that led to the discovery of the electron, then the proton, and the neutron in the atom, and how then you can look at different atoms on the periodic table, different elements, and see that they're comprised of different number of protons. We'll see that the elements differ, so what makes carbon different from oxygen is the number of protons in the nucleus of the atom. So it's the protons that really define the element or the atom. And then the electrons with the protons determine kind of the charge balance. And then as we get towards the end of the chapter, we start naming compounds. We start naming, ionic compounds. We name alcohols, hydrocarbons, things of that nature. So as we get to the end of the chapter, we do some naming. All right, so let's just end it here today, and we'll pick up with chapter 2 on Friday.
Actually, I got some problem with this. I think I remember, at first, in the lecture PDF, this is if we use plus or minus, we got the biggest way after the dot, right? But why in this class we're talking about this, the last question, this few questions, we talk about this one, why we can't just about 3 significant?
Well, because when you add and subtract, it's all about it's like the ones. So let me see your pen real quick. Just not the pen tip, just something I can point with. Let me use this. I won't write on the screen. So it's all about this ending in that ones placeholder. This the tens placeholder. This is a greater quantity. The ones placeholder is where we need to round to. So that's why when I did the math, I was tens place. sig figs times 2 sig figs, multiplication of addition, subtraction. I don't count sig figs, I don't think that place. I'll use the greater quantity in rounds. That's why I stack up the relative to the decimal place. Like if I had another example where, so if we do like 250, here's 2 sig figs, add to that 125.2. I'm doing here, around to this place.
I have two quick questions. The question about like the 50 and 75, is that going to be tested on the exams and stuff? Because it's technically against the rule, so to say. Are we using
Which
like
one?
common sense? No, when you did 50 plus 75, that's technically 2 sig figs, but if you rounded, you get 1 or whatever. Is that type of question going to be on exams?
Which one do you mean? So
I
like
did
where
50 plus 75 equals 125 right there.
I had a 125 minus 75
Oh,
equals
yeah,
50.
sorry.
Well, yeah, that's still 2 sig figs though.
Because I mean, but like it's 1 sig fig because of the addition rule, right?
No, it's 2 because of the addition rule. So like the addition rule is